In the last week, we started with a little introduction on reinforcement learning and on, or at least the main idea there. And the idea is that in contrast to the dynamic programming approach that we've seen in the last year, that we are learning something about what the optimal choice is and what the optimal or what the value function looks like by already playing a certain policy. So we are not an external viewer who analyzes the whole process as in the dynamic programming approach, but we are already included into the environment, into the law of motion, and we are executing an action inside the law of motion while we are actually learning what the value function looks like. So we are more or less much more inside the objective that we want to optimize than we were in the dynamic programming approach. We have then seen lots of vocabulary. We've encountered policies, we've seen greedy policies, so policies that choose the optimal action, so the action that maximizes the current value function that we have. We have seen epsilon greedy policies, so policies that deviate from that a bit. And we have seen the first algorithm that was the Monte Carlo control for estimating the value function. And after that, of course, if we have estimated the value function, we can then of course, derive directly also the optimal policy. This algorithm is a bit more complex, much more complex than would be necessary for solving the exercise that is coming directly after that. So the idea of the algorithm, again, is that we create a whole episode of the game. So we need a game that we can play repeatedly in repeated episodes. And first of all, we generate a whole episode of the game. So starting at S0 and A0, so the states in time 0 and the action we choose according to a policy in time 0. And then going overall the capital T episodes of the game until the game terminates. And after that, after termination, we start to update our knowledge of the value function. And in the case of the exercise that you will continue to work on in a minute, that is very simple because we only have episodes that contain of a single action, namely choosing one of these capital I, so one of these 10 lotteries. So generating the episode in the case of the exercises is very simple and very short. And after that, of course, this one down here is also not a loop anymore because the action only consisted of a single, the game only consisted of a single period of time. So this one isn't a loop as well. So we always switch between choosing an action and updating our value function here. All right, does anybody have any questions regarding the exercise or regarding anything we've seen before that you want to discuss here?
Honestly, I'm still struggling and I'm still a little bit puzzled, but I'm in a state of being puzzled that I'm not able to ask a proper question.
Okay, that is sad.
Yeah, that's true.
So what's puzzling you the most then?
Well, I think I'm still struggling with the general approach, right? I mean, what we did before was we had some general idea of a utility stream, right, that we could maximize, and this we started with. Basically, implicitly we started with an arbitrary policy by assuming what the value function is. This is the same here, right?
Yep.
And what we then did is we basically used this function to iterate over different choices, right? So we did things, and the general algorithmic approach, I think, is the same, which is good. But what puzzles me in a sense is I think sometimes at least in my view, the somewhat different terminology And sometimes I'm for example, if I look in this relatively simple, maybe not simple, but this problem, right? Then I mean, S are the states and A are the actions. So are the actions things that I do, or are the actions probabilities that I pick, or is it both, or is it that doesn't really matter what it is? I do not see where's the definition of the value over those episodes. Are those episodes things that I want to maximize the sum over one of those episodes? Or what is the objective in terms of episodes? These are, for example, I mean, but maybe this is due to my ignorance. I'm not. Maybe most of you just know what to do, and I'm just the only one. But which is okay. I have to deal with that.
Okay. Just starting with the question for the action A. The A's are the actions that we actually do. So the actions we actually choose to take. So what either is optimal.
Laundering one.
Pardon?
Or 2 or 3 or 10.
I just didn't hear you because my connection was. I lost the connection for a second.
So speaking in terms of this lottery choice,
yeah,
that we were just talking about, there are 10 different lotteries. So the A0 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
One of these numbers, yeah. As we had before, where we saved money and the capital stock grew and so on. So this is similar. The objective is actually the same as before. So it's very general. We maximize the total rewards or the discounted sum of rewards. That's why I didn't put it there, because the objective that we have in reinforcement learning didn't change from the objective that we've had before, but it always depends on the exercise we're looking at. So sometimes we're maximizing utility streams, sometimes we're maximizing actual income, sometimes we minimize the distance a car travels around a corner and so on. So we're always maximizing or minimizing some objective function.
But when you're just saying in this example with the 10 lotteries, then there's only one episode, so there's only S0 and A0?
Yeah.
But what is then the so there's no sum involved, right? I just pick.
No,
so there's no
okay, there is a sum involved. There might be a sum involved. An episode can contain of different time periods. So if you want to, for example, maximize the discounted cash flow from these lotteries over 10 days, so to say, what's called an episode does not necessarily I see. I mean, in this case, in this very simple case, I think there is no discounting because we are only considering a single point in time. So what we are then maximizing is the expectation, the expected value of our outcome. So in this very simple example, if you had to play like 10 lotteries after each other, and you would do that every day just once, and after these 10 days you would update your knowledge, then you would have an episode of length 10, and then you could, of course, include discounting between the episodes.
Yeah, discounting is not necessarily the thing that bothers me. So what you are saying is in this example, we are trying to we do not know anything basically about the lottery, or what do we know when we pick?
At the beginning, we don't know anything. We know there exist 10 different lotteries.
Okay.
Nothing
so
else.
Then I sample one. So this is my A0.
Mm-hmm.
Say I pick, I don't know, lottery 7. So right. A0 is 7. What is the S0 then?
S0 you could either say S0 is non-existent or S1 is non-existent. So you could either you start with a random lottery and then, so the state in this case is equal to the action in this very simple case.
Okay. So this will be 7 of I don't know, lottery 7 for example as well.
Yeah.
Then
it's not really an intertemporal problem here. That's I see that this is maybe not the best example because it's not an intertemporal problem. Yeah.
Yeah, I think that's the main point here. What we have here is a static problem. We don't have any intertemporal choices. So the on policy first visit control is actually choosing the best option in a static case. So an episode here is not really an episode because what you understand as an episode is something which lasts more than one period. So it's finite, but it lasts until capital T, which typically is larger than 1. So that's the maybe the difficulty with this exercise here. But of course, setting capital T equal to 1 is absolutely legitimate. Why shouldn't we do that?
Yeah, true. But the thing is, so state and action is then identical in this example.
Well, you don't need the state here. The state is only relevant for the intertemporal choice, I think. So here the state is really not necessary. So usually you have the sequence state, action, reward, then new state, new action, new reward, and so on. But here you have, well, some starting state of the world, which is irrelevant here. You choose an action and that's it. You get the reward and that's it. And then you stop. Then the episode is already over.
But if you just do this once, then there's no learning involved, right?
That's right. There's no learning involved.
So you just, but then the best thing is just pick at random anything.
Which is what you do when you start. But then you look at the next episode. So the learning only evolves.
But this again is an intertemporal thing because it's the next episode, right?
No, the next episode starts in T0 again.
Okay, but then this seems to be a trick, no? Because we were saying that the learning is, or the big thing of learning is that you learn on the fly. But now there's no learning on the fly because you just I mean, what is then the objective? Is it then again the sum over all those situations? So if you move again to you play again time 0, but what is then your objective that you target the reward of all those repetitions? This is the case? Or what is the objective?
To maximize the expected reward from your policy. So from choosing any of those 10 lotteries.
For a single episode.
In a single episode.
But isn't it my objective to pick the best, like the best, how to say, policy?
Yep. But so you pick the optimal, or you derive the optimal choice by learning what the best policy is, by maximizing the expected outcome or the expected reward from choosing any of those lotteries. So any of those 10.
So it's just pretty much like, how do you say, an Entscheidungsbaum. So you just calculate for every option, you calculate the best reward, and then you pick the best option step by step.
That would be what a human would most likely would do, yes.
But isn't it the same?
Play everything once and then decide which of those is the best. This, of course, holds true in this super simple, maybe too oversimplified scenario. If you are in a more complicated scenario where lotteries are not just lotteries that pay you random amounts of money, but if you have a real intertemporal problem there, then you wouldn't go with a decision tree like.
Okay, but in our example, we would just do this.
As a human being, as a rational human being, you might want to do that, yes.
Okay.
But the idea here is to try and apply this algorithm, see that it doesn't work, actually doesn't work really optimal, but to get a first hands on this algorithmic structure and on the idea of generating episodes, and after that updating the policy/value function.
Okay. Thank you.
One question, learning also happens between episodes, right? Not between times. I think what Jörg mentioned is maybe that learning happens maybe in T1 you see, oh, that didn't work out as well. And in T2 you choose something different and then you learn. But that's not true, right? In this case, you learn between the episodes. And one episode is from T1 to capital T.
Yes.
If we have an intertemporal problem.
Yep. With this Monte Carlo methods, with Monte Carlo methods in general, you only learn between episodes. You don't learn within episodes, which is a severe problem, and we'll see that in the second half of today.
Yeah, I think that's relevant here to mention that you're absolutely right. With using this particular algorithm, you're learning between episodes and not over or in time. But there are other algorithms that we also getting to know, going to get that we are also learning soon.
Okay. Nevertheless, I'd like to start with the exercises then. So I don't know how much this is going to take, but I think we can try with half an hour and then have a look at the results later. So see you. Okay, welcome back, everyone. Welcome back, everyone. I'd like to just go over the solutions. Still people coming back. Oops. All right, welcome back, everyone. I'd like to go over the solution briefly and then show you with a Shiny app what is not really working properly and where we could optimize this procedure with the algorithms we see in the next week, Thursday. So the idea here is, I hope this is large enough for everybody to read. We just initialize everything, so we have 10 lotteries, we have a deviation probability of 1%, we have 50 episodes. We initialize pi with this solution 0.1 for each lottery, but it doesn't really matter because we don't need to normalize probabilities. And this one here is just a storage of the actions that we take around these over these 50 episodes. And the rewards is an empty list that contains that prepares vectors in each list element for all the rewards of the respective lotteries. So that's our objects we need to initialize. And then we can go in a loop over all our 50 learning episodes. And in each episode, we first of all run the episode. In this case, just decide over a single lottery. So we sample from 1 to capital I, so one of these 10 lotteries, a single time with probability equal to our policy. The policy we initiated was totally random, so this one is totally at random in the first case, in the first episode. After we decided for an action, we have to update the reward list of that action by taking the reward list itself and appending the action, the reward of the lottery we just played, and the lottery we play has expectation equal to the action we choose, because the action is lottery 1 to 10, and that's also the expectation of the lottery. Then we can use the sapply function to compute the mean of each element of this list. So this is very straightforward and very easy to get the value function from these rewards. Just use sapply of the reward list and tell R to compute the mean of this list. And this gives us the value function already. Or more or less, not the value function, but the action value function according to choosing one of these 10 actions. Once we have that, we need to update our policy. And we can do this in a two-step procedure. First, we set the policy to epsilon divided by the number of non-optimal actions. And then we override the policy at the position of the optimal action, so at which max the values. And we set that one to 1 minus epsilon, so in this case to 99%. And then we store our action that we chose in actions at position I to be able to plot the action later on. And if we do this, we see, if we do this once, we see that in this case, this algorithm only chose the second lottery every single time. It didn't deviate a single time, which is in the end a not very good outcome, not the outcome we want to have, because we already know from exercise A and from the context of the exercise that action 10 would be optimal. And the reason for that is, of course, we have a very low number of episodes we play, and we have a very low probability of deviation. We can play around with both a bit. And I wrote this little Shiny app, so you can have, or we can play around a bit with the number of lotteries, the number of episodes to run, the deviation from the greedy policy, and the initial value guess, which is also something we can use in order to learn quicker. So let's just, let's just reload this. You can also, the link is in the slides, you can also use the Shiny app yourselves. So let's just run this Shiny app with a deviation that is equal to 1% or roughly 1%. This on the left is log scale, so this is about 1% of deviation probability. And in here we see that we were lucky and we learned the value function in here that contained the 10th lottery because we had 100 episodes and we deviated once or either to the 3 or to the 10. We can't see that anymore, but we've learned the perfect policy. We can learn again, and then we see we didn't learn the optimal policy. We can learn this again and see the policy we learned isn't working very well again, and so on. We can do this very often. We can do this, say, 100 times. And then we can get a distribution of what we would obtained if we run the whole learning process 100 times. We would see that in some occasions, in many occasions, we learn the optimal policy, but in very many occasions, we don't learn the optimal policy. And if we run this really often, we would see that the outcome of this learning mechanism is not really what we would like to see. Because we didn't deviate, for example, we didn't deviate much from the greedy policy. If we increase the deviation from the greedy policy to 5% or even to 10%, and we learn lots of times, then we see that we very often learn the optimal policy and never learn any policy smaller than 5. So every time with 100 episodes and a deviation probability of 8%, we learn at least a policy in here, in this example, that is larger than 5, which is quite good. But the average reward we would get following this policy is a little smaller than 9. So in many cases, we don't learn the optimal policy. And even if we learn the optimal policy, we deviate from this optimal policy with quite some probability, namely a little bit larger than 8%. So even if we learned in the end the perfect policy, we would still deviate from this policy due to our epsilon greediness.
May I ask something?
Yeah, sure.
Could you just quickly describe me or explain me the difference between number of episodes and learn 1,000 times? I mean, learn 1,000 times means I play 1,000 times those 100 episodes.
Yep. And each time after 100 episodes, you store the policy, and then you restart the whole process again from zero and learn again. So it's this learn 1,000 times is just to evaluate the learning process itself. It doesn't make the learning itself better.
I see. So this is not identical to say I ramp up the number of episodes to 100,000 times.
No. Okay. It's different. We can also increase the number of episodes to, now it's 6,000 episodes, and if I learn a single time, we already see the value function is the correct value function, and the learn policy is always the correct policy. But of course, we have increased the number of episodes we run, so it took more time, which is not a problem with this very simple example, but in larger applications, time is, of course, a constraint, and you cannot run as many episodes as you like to run because you're only learning by analyzing data, and you, of course, don't have an infinitely large data set. So this might be a restriction here, but in this case of this simple simulation, we can, of course, loosen this restriction. Okay. We are still having 10 minutes, and I'd like to use
statistics.
This is the link again to the Shiny app that I just launched for you. You can play around with that yourselves if you'd like. What we have seen so far is an algorithm or a class of algorithms that were only able to learn once an episode had finished. So we don't learn anything before the episode finishes, which is very disappointing and unpleasing because some tasks might just never finish if you just do them totally at random. So choosing a lottery, of course, always finishes, but if you're looking, for example, at this little picture here, if you want to ride your bike or ride your self-driving bike around this parkour here, and you try to do this completely at random, and after that want to evaluate your actions, then you might see that this is rather difficult. Let's have a short look at this example. We have lots of states, namely we have x and y coordinates. So we have 100 different x coordinates, 20 different y coordinates, and we have the speeds in x and y direction. So we can be either traveling from -5, that is 5 units to the left, to +5, that's 5 units to the right, in x direction, and the same goes for the y direction. And the control in here that we have, or the actions that we can choose, is to either accelerate or decelerate in either direction. So the action, we have 9 different actions here as well. So the dimensions of our action value function is then 100 times 20 for the coordinates on the grid, times 11 for the speeds in x direction, times 11 for the speeds in y direction, times 9 for the size of the action set, which leaves us in a state action space of roughly 2.2 million elements. Now this is an example where going over all the potential states and computing the expected rewards or the expected value function in a dynamic programming approach is already very, very time consuming, because you would need to do that for all 2 million elements in each iteration of the dynamic programming approach, in each value function iteration. On the other hand, doing this completely at random, going through the maze here, is also very time consuming. You can see this. After 100,000 iterations at day 1 at 9:30, of course, we are not finished. After 54 million iterations at day 1 at 6:30 p.m., the algorithm still didn't finish, and after 153 million iteration at the end of at the noon of day 2, this algorithm, randomly finding a way through this maze, still didn't finish. So doing this purely at random also doesn't work, and doing this with dynamic programming doesn't really work as well, because it is also very time consuming if you you would need lots of iterations because you would only learn something about the value function the first time in the area close to the finish, and then so on. It would also take a very long time. So we need an algorithm that's able to learn after each step within an episode. Or if we don't have episodal games, but games that go on for an infinite number of time steps, then we need, of course, some algorithm that allows us to learn in between and not just at the end of an episode. And these are called temporal difference learning algorithms. You can see here the very same maze with a temporal difference learning algorithm, an algorithm that is able to learn after each iteration. And as you can see, the first time this algorithm, it took the algorithm roughly 1 million steps to find a solution to go through this maze. So whenever the bike hits either one of these black walls or is outside the grid, it will be reset. And I just drew the last, I think, 500 or 100 steps going through the maze. So not quite roughly 1 million iterations for the first time. Then the second iteration, in the second iteration, it took the algorithm roughly 400,000 steps to finish. And in iteration 3 already, it only took 37,000 iterations to find a way through this maze. So 37,000 iterations, steps compared to the 2.2 million we would need to look at in dynamic programming is already in the third iteration a much faster algorithm, or is much faster in computing what we want to have here. If we continue this after just a couple of steps, 40 steps in here, we were able to find a solution that is already very close to the optimal solution. So we have some going around down here that isn't actually optimal, but the rest of the way looks actually pretty optimal, or at least pretty good, after then only a few seconds of computation, or a few minutes for the first 2 iterations. But after the first 2 iterations, everything is done in a fraction of a second. Now, how do these these algorithms, I said, are called temporal difference learning, and they work by having a look at the difference between the reward, the current value function, and the value function of our next state. So they basically do the same thing we did using the Bellman principle, but we're doing it right now not in expectation. So we don't expect don't compute the expected value function of tomorrow's state, but we just use the realization of the value function. We use the value function that we currently stored and currently computed of the realized next state. Just ignore the first line here with the Monte Carlo update rule, but let's have a look first at the temporal difference update rule for the value function. That is, our new value function is then computed as the old value function plus alpha times the reward we get from our action plus the discounted value function as of the state of tomorrow. Of course, we need to wait until the state tomorrow realizes, but after that has taken place, after tomorrow has realized, we can immediately start the learning process. And from this, we subtract the value function of the current state, because this is just the very definition of the value function. The value function is the reward of tomorrow plus the discounted value function plus the discounted continuation value function. So the discounted value function of the state that we will be in tomorrow. We call this delta the temporal difference error, because sometimes sometimes this one here is negative, sometimes this is positive. We'll see on the next slide what the positive or negative, what these mean. Now, if we have a look at the first bullet point here, then the corresponding Monte Carlo update rule would be to take the value function, so our current knowledge of the value function or current value function object that we have, and add the difference between what will turn out to be the total discounted sum of all the future rewards. So GT is what we just defined GT as the discounted sum of all the future rewards, minus our current knowledge of what the value function actually is. And the value function is, of course, nothing else than, by definition, the discounted cash flow or discounted stream of utilities, or whatever the context of the exercise is. So if the rewards that we actually receive from our policy is larger than the value function that we currently think is true according for our state, then of course this one here is positive and we should increase the value function of our current state. If, on the other hand, the realization of all the future utility flows or cash flows is smaller than our current estimate of the value function or our current knowledge of the value function, then we should decrease the value function. We multiply this with alpha, which is our learning rate parameter, and as epsilon is our deviation parameter that determined how much we deviate from the optimal policy. Alpha is our learning rate parameter, which determines how fast we are adapting our value function to any kind of deviation from what we've already learned. We will go over the convergence rules and over the definition of the TD error in the session on Thursday, and after we did that, there will be also exercises on temporal difference learning and our first full temporal difference learning algorithm. Okay, do you have any questions left so far? Okay, then have a nice afternoon and see you on Thursday.